the very beginning of quantum mechanics, we have heard that the dynamical variables of classical mechanics are represented by Hermitian operators, and the operators are best represented in terms of matrices. So, if we have an operator which is Hermitian, it is represented by an Hermitian matrix. The dimensionality, if we have a Hermitian matrix, then it must be a square matrix. Then if n be the order of the matrix, then it will have exactly n eigenvalues. It has also been told that the operators of quantum mechanics are not finite dimensional matrices, they are infinite dimensional matrices. So, today's class we are using for the matrix representation of different operators, and we will show how they are. For number operator, first we consider the number operator. In the last class, we have seen that n operating on an eigenket gives you n times. So, we find that m n is equal to n times delta mn. This is the matrix element, and it is generally denoted as mn. If we want to know the matrix corresponding to n, so the matrix corresponding to n is actually comprises of the elements of its elements. So, the n matrix is actually given by this this is the matrix n actually. You know that this number, the second index, corresponds to the column index. So, this is the column index, and this is row index. We see that these elements, all these elements are 0 unless m is equal to n. That is to say, this matrix will be a diagonal matrix. And what will be its matrix form? When n is 0, it is 0. This is 1, this is 2, and so on and so forth. So, this is since there is no restriction on the n values, that is, a system can have any number of photons. So, this matrix extends up to infinity along its row and as well as its column. So, it is an infinite dimensional diagonal matrix. It is It is an infinite diagonal dimensional diagonal matrix, means only the diagonal element survives. Now we come to the second operator, that is the Hamiltonian, the operator of Hamiltonian. We know that Hamiltonian operating on an eigenket n gives you n plus half h cross omega n. So the matrix element is now so this is equal to n plus half h cross omega delta mn. Again, since the matrix, this is a diagonal matrix, it will be a diagonal matrix. So if we want to write Hamiltonian, you will see that when n is equal to 0, it is half h cross omega. So we write Hamiltonian operator as, we take h cross omega by 2 common. So the first term, n, this is 1, this is h00, so let me write h00, h01, h02, h10, h11. As we have taken this common, this is equal to 1, this is equal to 3, this is equal to 5. So the matrix is h cross omega by 2, 1 0 0 0, 0 3 0 0, 0 0 5 0 0, and so on and so forth. So only the diagonal element will survive, and they are the odd positive integers when we have taken this as common. So these are the two matrix elements, which both of which are diagonal. Now we shall go to the matrices for A plus and A minus, which are no more diagonal. They are not diagonal. Let me come to the matrix element for A plus and A minus first. The A plus operating on a state n gives you n plus 1 square root of n plus 1. Now if we calculate this one, m A plus n, it is n plus 1. These elements are written as A plus. For the convenience, I am writing plus in the superscript, and this is the matrix element. Now for non-zero matrix elements, we must have A m these elements will survive. that is for which the row index is 1 greater than the column index. This is row index and this is the column index. Only this element survives. So let me first see what is a matrix. A matrix is generally denoted by these elements 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1. You see, these are the diagonal block. So these are the diagonal block. If we move along one step of diagonal block, the one step of diagonal block elements are 1, 0, 2, 1, 3, 2, and the next one is obviously 4, 3. So if we move one step of diagonal down, then we will have the elements which has its row index 1 greater than the column index, exactly similar to this. And if we move one step up, so we call it one step of diagonal down, one step of diagonal down. As we move one step down from the off diagonal elements, there are another category. These elements, if we move one step up the diagonal, then we will have these elements marked in red color, in which case the row index is 1 less than the column index. So we mark this element as one step of diagonal up. So it is found that the matrix elements for A plus operator belongs to this category. So we write the matrix element for A plus we first write the diagonal elements. These diagonal elements are 0, 0, 1, 1, 2, 2, 3, 3. Now we have 1, 0, then it is, so this is square root of 1, square root of 1, 0, square root of 2, 0, 0, square root of 3, and the rests are 0. This is the matrix element for A plus. Similarly, if we go to the matrix elements for A minus, operating on n gives you n times n minus 1. So this is m A minus n is equal to n. The orthogonality demands for non-zero matrix elements A minus, we must have that is, these matrix elements are A minus n minus 1 n. So these matrix elements are those one step of diagonal up. So the matrix for A minus, this is the matrix for A plus. Similarly, the matrix for A minus is this is 0 0, then 1 1, then 2 2, then 3 3. Sorry, this is 0, and so on and so forth. This is the matrix of A minus. With this knowledge of A plus and A minus, now we shall go to the very important matrices, that is the matrix for X and P's. We shall require these two relations. We know that A plus is 1 upon root 2 Q minus IP, and A minus is equal to 1 upon root 2 Q plus IP. If we add these two, we get A plus plus A minus is equal to root 2Q, or Q operator is equal to 1 upon root 2 A plus plus A minus. So by adding these two matrices, we can get the matrix for Q. And similarly, if we subtract this to A plus minus A minus, we will have minus I root 2 P, or P operator is equal to when we take I on the numerator, in an earlier class we have missed this I factor, so this factor actually came as A minus A plus. Please make the corresponding correction. And that led to a term which is incorrect due to this I factor, minus I factor. So the operator for Q is actually 1 by root 2 times 1 by root 2 times the 1 by root 2 times the sum of the matrices for A plus and A minus. This is 0 0, then we will have 2 2, we have 3 3. Now the matrix, if we go down this is root 1 0 root 2 0 0 root 3, and on the other hand then root 2. Etc. These are the matrix for Q, and if you want to get the matrix for position, then X is Q is equal to, you know that Q is equal to H cross X, or X is equal to so if you multiply it by this factor, we will get the matrix elements for X. It is also an infinite dimensional matrix. For P operator, there will be an I factor, and these upper of diagonal elements will be followed by a negative sign. So we have constructed the matrix for few common quantities like the position, momentum, Hamiltonian, number operator, and the raising and lowering operator in connection with simple harmonic oscillator. And we have come to the conclusion that all of these elements are all of these matrices are infinite dimensional matrices. Infinite dimensional matrix. The matrix for N and H are diagonal ones. The matrices for A plus and A minus are one step of diagonal, and for Q and P, the elements just adjacent to the diagonal elements contributes.